have some pretty strong feelings about traffic and rainy weather that I think are pretty relatable to other people. Things like people running red lights, not indicating and swerving into other lanes seem magnified. It feels like the rain brings out all the crazies, and it feels pretty certain that there's a connection between the two. But if you were to ask me if traffic and rainy weather is crazy according to the data, it's not as straightforward. In fact, there's a lot of uncertainty, starting with how do you even quantify crazy? I'm Lily, I love data, and in this video I explore how we can use data and math to frame and answer this really big question. And I break it down into smaller questions that are more quantifiable. Comparing data on non-rainy days versus rainy days. Does rainy weather put more vehicles on the road? Does rainy weather make traffic slower? And does rainy weather cause a higher rate of accidents? Along the way, we'll also answer questions like, what are statistical significance and Bayesian statistics? What does rainy weather traffic look like around the world? And how big of an impact does the El Niño cycle really have on rain and traffic? The answers may or may not shock you. So our first question is, does rain put more vehicles on the road? The idea here is, if we know how many vehicles there are in a given location per day over time, and look at these values in a distribution, we can see the shape of the daily vehicle counts that occur most frequently and less frequently, and how spread out they are. And if we have two distributions, one with just non-rainy days and the other with rainy days, then we can compare whether they're significantly or credibly different. More on that language later. I was able to get daily vehicle count data for the Greater Sydney area from a government resource. They have almost 2,000 of these traffic count stations around New South Wales, and there's data available dating back to 2006. I stitched this together with daily rainfall data from the Australian Bureau of Meteorology, who have 17,000 stations around Australia which measure rainfall. Some of the older stations have been collecting data since the late 1800s. Now, the data has some limitations. As with any dataset, there was missing data and some dirty data, which we can work around. The much bigger limitation was that the rainfall data was measured each day at 9 AM and recorded the total precipitation for the previous 24 hours. So I was working with traffic and weather data that didn't exactly line up. I tried aligning the traffic data to 9 AM to 9 AM and turned it into gibberish. I don't think it makes sense to split up what's happening in peak hour traffic at 8:59 to 9:01. So take my findings about specific locations with a grain of salt. But the more important part, the methodology of how I use the data, still stands. And with this framework, we could plug in better aligned data. The first part of my methodology was narrowing down the number of years to analyse. Because traffic volume changed for a few years after COVID and rainfall changes every few years with the El Niño cycle, I decided to focus on the last 6 years between 2018 and 2023, which captures 3 years impacted by COVID and 3 years not, and 3 years of a rare La Niña event and 3 years outside. And across the 6 years, we have a healthy sample size of non-rainy and rainy days. Then I narrowed down the traffic and weather stations. Rainfall is very location specific. There's varying levels of correlation in rainfall between different weather stations. 2 different locations in Sydney could have very different amounts of rainfall in millimetres in a given day, or it could be raining at one location and not the other. In fact, the Bureau of Meteorology provides rainfall forecasts within a 3 km square around a given location. This means that in order to identify rainy days for a given traffic count station, we should be using rainfall data from a weather station close by, and I stuck to the 3 kilometres that the Bureau of Meteorology uses. So even though there's a lot of traffic count stations in the Greater Sydney area, only 26 locations were within a 3 kilometre proximity of a weather station and had data for the last 6 years. Some locations have traffic stations tracking vehicles going in both directions, so in total I analysed 36 traffic stations. Lastly, daily vehicle counts have a lot of variability. There's low days and high days, even when you're only looking at one station. At this station, for example, we have 2 peaks of what the number of vehicles are most likely to be in a day. We want to know if, as a whole, rainy days are different to non-rainy days, and averages don't tell the full story. For example, you could have your non-rainy days look like this, and your rainy days look like this, where you can see a higher concentration in this second peak. But the averages, which can be easily skewed by outliers, could be very similar. This is why I decided to compare distributions to see how different the overall shapes are. And because these distributions are unique to each traffic station and rainfall is location specific, I also decided to do this comparison at a traffic station level so that it'd be cleaner and easier to identify any differences between non-rainy and rainy days. Okay, so if we have our two distributions per station, how can we quantify how different or not different they are? Statistics gives us two ways to conceptualize this: the frequentist approach and the Bayesian approach. And it's important to understand the thinking behind both of them because they answer our question in different ways. Let's start with frequentist statistics, which is where the concept of statistical significance comes from. The frequentist approach is based on the philosophy that if you run an experiment like flipping a coin repeatedly an infinite amount of times, the distribution of your results, in this case the proportion of times it lands on heads, would look like this: a normal distribution of all the possible results. Sometimes you'll have gotten heads less than 50% of the time, or more than 50%, but from an infinite number of flips, the mean, 50%, is the most frequent, most probable result. In the frequentist approach, probability is defined as frequency. This philosophy assumes that this mean, mathematically denoted as mu, is fixed. There's a true value for it out there. We may not know it because we haven't flipped a coin an infinite amount of times, but we can estimate it with data from random sample flips. And the more samples we get, the closer we can get to knowing what this fixed true value is. For our problem, instead of trying to estimate how probable it is to flip heads, we've got our two groups and we're trying to estimate how probable it is that they're not different. Or in other words, we're trying to estimate how probable it is that they are different. A common frequentist method used to compare whether there's a difference between groups is null hypothesis significance testing. It calls for us to frame our hypothesis like this. Our null hypothesis would be there's no difference in the number of vehicles on rainy days. There's no effect from rain. Our alternative hypothesis would be there is a difference in number of vehicles. There is an effect from rain. Next, we assume that the null hypothesis is true. What does that mean? If we were to take an infinite number of samples of daily vehicle counts from non-rainy days, and the same from rainy days, and we calculated the difference between these two distributions, we're assuming that this mean here is 0, that there being no difference is the most frequent, most probable result. Let's focus on this third distribution. Now, still keeping this assumption in mind, we can bring in sample data of the two groups we want to compare. Our daily vehicle counts on non-rainy days versus rainy days in the last 6 years, where each daily vehicle count is a sample. Taking some parameters from these two groups, the sample sizes, means, and standard deviations, we can do a t-test and calculate a t-statistic, which we can plot on this normal distribution as a measure of how far away our observed sample result is from the mean. This t-statistic corresponds to a p-value, which represents the region on this curve that's outside our observed result. This can be interpreted to be the probability of getting the same observed result or a result that is further away, more extreme from the mean. If this p-value is smaller than the level of significance we set, for example 0.05 for a 95% confidence level, and in this example it is, we can say, in the world where the null hypothesis is true, where there is no difference in number of vehicles on non-rainy and rainy days, there's a less than 5% probability of getting the observed result we did or a more extreme result. Because of this, we can reject the null hypothesis and say with 95% confidence that there is a statistically significant difference in the number of vehicles between non-rainy and rainy days. This gives us a yes/no answer of whether there's a significant difference. It's a threshold test of, is the probability of getting sample data that's the same or more extreme low enough? How can we quantify how different non-rainy days are from rainy days? And is it different enough for rainy days to feel crazy? For this, there's a few more things we can do. The frequentist approach gives us the math to calculate a confidence interval around the difference in means of our sample groups. With this sample data, at a 95% confidence level, we can estimate that there are between 200 and 1600 fewer vehicles on rainy days. Note that these are just endpoints. And we can calculate an effect size, which is the measure of how different the means of our sample groups are in terms of standard deviations. For example, an effect size of minus 0.13 would mean that the rainy days group is around a tenth of a standard deviation lower than the non-rainy days group. Mathematically, this would be considered a small difference. For reference, around 0.5 would be considered a medium difference, and above 0.8 would be considered a large difference. But there's even more we can do, which is where the second approach, Bayesian statistics, comes in. It's based on the philosophy that we may never know this fixed true value, and that's okay. Instead, we can start by modelling our background knowledge, if we have any, of what daily vehicle counts are like on non-rainy and rainy days. This is called a prior belief, and here's some examples. We could have no concept whatsoever of what daily vehicle counts are like, so we could model an equal chance of them being any value through to infinity. Or we could have a bit of background knowledge and expect that daily vehicle counts are between these values, and they're more likely to be here rather than here, so we could model this as a curve. Or we could have lots of background knowledge and expect that daily vehicle counts are concentrated here. For my prior belief of daily vehicle counts on non-rainy days, I'd never looked at traffic data before, so I went with this broad shape between the minimum and maximum values in our 6-year dataset. Now, if you knew that there are more vehicles on rainy days, you could model this into your priors. But I didn't know that, and I used the same broad shape for both. We can then bring in our sample data and use our priors to estimate parameters like the population means and standard deviations for these samples. This is done using a computer by taking each of the values in our priors and each of the values in our sample data and simulating thousands of samples, close to all possible outcomes. And from this, we can get these 95% highest density intervals of the population mean. Or we can think of this as our 95% most likely daily vehicle counts for non-rainy days, rainy days, and the differences between the two. In my analysis, sometimes these intervals were similar to the confidence intervals from the frequentist approach, but here we get a distribution of which outcomes are more likely and even most likely. For example, at this station, the most likely differences are between 192 and 1,600 fewer vehicles on rainy days, and the most likely difference is 930 fewer vehicles. If 0 were in this highest density interval, we could say that there being no difference in the number of vehicles is one of the most credible outcomes. But it isn't, and we can say that there is a credible difference between non-rainy days and rainy days. In the Bayesian approach, probability is defined as degree of belief. These values aren't fixed, and we can always keep updating our prior and posterior beliefs with more and more data. And we can understand what's going on right now with what we know. So now we have a suite of methods to estimate whether vehicle count is different on rainy days and how different. But not all rainy days are the same, and not all traffic days are the same, which is why I also segmented the data to look at different days of the week and weekdays versus weekends, because traffic on a Tuesday can be very different to traffic on a Saturday. Different rainfall intensities, days with no rain versus light, moderate, and heavy rain, based on how the Bureau of Meteorology classifies this, because these could have a different impact on people's decisions to drive. Similarly, how many days in a row it's been raining. Some quick clustering gave me some nice bands, days with no rain versus 1 to 2, 3 to 5, and 6 to 19 consecutive days of rain. Alright, 36 stations, let's go! This station in Penrith has significantly incredibly more vehicles on rainy days overall. The p-value is smaller than 0.05, and 0 isn't in this 95% highest density interval from our Bayesian sampling. The most likely difference is 684 more vehicles on rainy days. Or if we take this 684 and divide it by the average number of vehicles on non-rainy days, this works out to be 7% more vehicles on rainy days. Looking at the effect size, this is a small difference. The station also has significantly incredibly more vehicles in specific conditions, like on Sundays and Thursdays, on moderate rain days, and after 3 or more consecutive days of rain. These are medium differences, and the most likely differences are between 9 to 15% more vehicles on rainy days. A few side notes here. I apologise for the small font. There's a lot of data to fit in here, and it's going to be tiny town for a few more minutes, so that you can pause and zoom and look at the numbers if you want. Speaking of tiny, the sample sizes can get pretty small when you segment the data, and here we only had 19 days that were between 6 to 19 consecutive days of rain. Without the Bayesian sampling, I would say take these frequentist results with a grain of salt because of that small sample size. But with the Bayesian sampling, where we've generated thousands of samples, this is good support for what we found with the frequentist methods, and it's even given us a narrower interval based on our sample data. These 4 stations have more vehicles on rainy days only in specific conditions. These are small differences. This station in Moore Park has fewer vehicles on rainy days overall, and in specific conditions like on Sundays and Fridays, on moderate and heavy rain days, and between 1 to 5 consecutive days of rain. Most of these are small differences, except here on heavy rain days, where the most likely difference is 8% fewer vehicles. This is a medium difference, but note that this being a medium difference is influenced by the sample size of heavy rain days being very small at 22. There are 9 other stations like this. Most of these are small differences, except here on heavy rain days and here on Thursdays, Fridays, Saturdays, where the most likely differences are 5 to 8% fewer vehicles, and these are medium differences. These 7 stations have fewer vehicles on rainy days only in specific conditions. Again, most are small differences, except here on heavy rain days, where the most likely difference is 25% fewer vehicles. This is a large difference, but based on a very small sample size of 21. This station in Blakehurst can have either more or fewer vehicles on rainy days depending on the conditions. There are fewer vehicles on rainy days overall, on weekends, on Sundays, Tuesdays and Saturdays, and days 1 to 2 of consecutive rainy days. On the flip side, on days 6 to 19 of consecutive rainy days, the most likely difference is 7% more vehicles. These are all small differences. There are 7 other stations like this. Most are small differences, except here where we have medium differences, this one being based on a very small sample size of 21. As a comparison, this station in Redfern has no significant or credible differences on rainy days. Visually, we can see that the distributions for non-rainy and rainy days have a lot of overlap. Our p-values are greater than 0.05, and there being zero difference in the number of vehicles is one of the most likely outcomes. There are 5 other stations like this, and these are their results from non-rainy versus rainy days overall.
Whoa.
Let's address the uncertainty in these findings. Firstly, the timing of the data is and even if the days did line up perfectly for the traffic and weather data, we can't really pinpoint the influence of rain at a specific time and vehicle count fluctuations. I did also do this analysis with the traffic data aligned to 9 AM to 9 AM, and separately I looked at it at an hourly level with a different rainfall data set from 2017, and the findings were similar. Significant and credible differences only at some locations, sometimes. Secondly, we haven't really proven causality between rainy weather and number of vehicles. There are so many other factors that influence the number of vehicles on the road on any given day, and our findings could be complete coincidence. And lastly, we're dealing with a lot of individual decision making. Like, I can imagine some people would forego a discretionary trip if it's raining, and other people would decide to drive because it's raining, and everything in between. Some days it'll tip to more vehicles on rainy days, some days fewer, and we're trying to fit all of this big human behaviour into neat buckets of statistically more, fewer, no difference. But if we take these findings at face value, the overall takeaway is rain puts more vehicles on the road at a handful of locations. At most locations, rain either put fewer vehicles on the road or there was no significant or credible difference. This doesn't explain the pervasive feeling that traffic is crazy in rainy weather. I feel like no matter where I'm driving in the rain, it feels crazy. So are people driving super slowly on rainy days or what? Our second question is, does rainy weather make traffic slower? The idea here is, if we know how long it takes to travel from point A to point B per day, we can again compare the distributions of non-rainy days and rainy days. I was able to get this data from TomTom, who collect GPS data from their navigation products to power their analytics tools. These tools are marketed to city planners and traffic authorities, but using a free trial, I was able to plug in routes along the same roads as 20 of the traffic count stations I analysed earlier, and get the median daily travel times for 3 different day parts: morning peak, afternoon peak, and off-peak, for the month of October 2022. I stitched this together with the daily rainfall data from earlier, which measures rainfall from 9 AM to 9 AM, so take this with a grain of salt, but here's what I found. For this station, I analysed the median travel times along this route going in both directions. There are significant and credible differences on rainy days in specific conditions. On moderate rain days in off-peak hours and on days 3 to 5 of consecutive rainy days in off-peak hours, the most likely differences are a 12, 13 or 17 seconds shorter travel time on rainy days. Going eastbound, on days 6 to 19 of consecutive rainy days in morning peak hours, the most likely difference is a 38-second longer travel time on rainy days. There's a few things to note here. Firstly, looking at the effect sizes, these are large differences, but they're based on tiny sample sizes, which we'll come back to later. Secondly, because of these small sample sizes, even though these are statistically significant, we're really leaning on the Bayesian sampling to get these most likely differences. Thirdly, you might be wondering whether a station having more or fewer vehicles on rainy days impacts travel times. Well, from our previous analysis, this station didn't have significant or credible differences in the number of vehicles on rainy days, and this station had either more or fewer vehicles on rainy days depending on the conditions. However, unfortunately for these stations and the next few stations I'm going to show you, there's missing data for daily vehicle counts in October 2022. So the relationship between number of vehicles and travel times is unknown. There are two other stations that have significantly incredibly longer travel times on rainy days in specific conditions. These are medium and large differences, with the biggest one here, where the most likely difference is an almost 2-minute longer travel time, but again, all based on tiny sample sizes. Those were the only stations with significant and credible differences, but this analysis has some big limitations. The first is I was working with a really small sample size. There's only 31 days in October, and the groups get really tiny when you split it out into light, moderate, and heavy rain days, for example. Some stations didn't have any heavy rain days that month. The second limitation was again the timing of the data, but even if the days did line up, it'd be better to look at travel time and whether it was raining that hour or in increments of a few minutes. Luckily, there's a few studies from around the world on exactly this that can supplement my dodgy findings. Here are 7 studies on the impact of rain on traffic flow from the last 20 years. I tried to get a good mix of different countries from around the world, and as you can imagine, their methodologies all varied, like how they measured traffic conditions, how far away weather stations were from the traffic they studied, and the length of periods analysed. Importantly though, even though they were slightly different, they all looked at increments of 1 hour or smaller to marry up traffic conditions to rainfall at the time. And despite these differences in methodology, the findings were pretty consistent. 6 out of 7 studies found that rain reduced capacity, which is the maximum number of vehicles that can pass a point within a specified time period, and free flow speed, which is the average speed of vehicles under low volume conditions or without congestion. This study tracked individual number plates around London and found that rain increased total travel times. 5 out of 7 studies found that these effects increased with rainfall intensity, although the definitions of light, moderate, and heavy rain also differed. So there's some good evidence to support that rainy weather does make traffic slower.
Oh my god! Oh.
In my professional opinion, slower traffic sucks. If you're driving in the rain for an hour or more, a 5, 10, 15% longer travel time can add up. And over, say, a year, that's a lot of extra travel time. But on its own, is a longer travel time enough for a trip to feel crazy? I feel like craziness is the compounding of this is taking so long and people are driving shit and you're really gonna do that? Our third question is, does rainy weather cause a higher rate of accidents? The idea here is, if we have the proportion of road accidents that happen in different weather conditions and compare this with the proportion of time it's rained, we can see if there's a disproportionately higher rate of accidents in rainy weather. And wouldn't you know it, there's a New South Wales government data set for reported road crashes, and it has some really interesting data points like where and when it happened, what kind of road or intersection it was at, what the lighting and road surface were like, and what the weather was like. I was able to get this data for the same 6-year period of 2018 to 2023. This is the split of crashes that happened when it wasn't raining versus when it was raining, by year for Metro Sydney as a whole. There are some conditions where we see an over-index of rainy weather crashes, when the natural lighting was darkness as opposed to daylight, dawn or dusk. Going hand in hand with this, when it was between 8 p.m. and 2 a.m, when the road was curved as opposed to straight. In some years, when the crash was at specific types of intersections, like an L junction, when a motor scooter was the key traffic unit involved in the crash, and when the speed limit was 110 kilometres per hour, which is the highest speed limit in New South Wales. This all makes sense and speaks to higher risk levels in rainy weather due to impaired visibility and slipperiness, particularly at high speeds. Let's focus on this Metro Sydney total again. If we compare this to the percentage of days it rained in these years across 8 different weather stations, it looks like crashes in rainy weather is disproportionately low. But when it's raining, it usually isn't raining every hour of the day, so the proportion of days rained doesn't accurately capture the proportion of time rained and the opportunity to have an accident while it's raining. So I also tried to look at this at an hourly level. Each crash in the dataset had a label of the 2-hour interval it occurred in, and that hourly rainfall dataset I mentioned earlier, that came in handy here. It had rainfall data from 12 different weather stations in Metro Sydney in 2017 to 2018. Now if we compare the percentage of crashes that occurred while it was raining in these 2-hour intervals in 2018 with the percentage of times it was raining in these same intervals in 2017 to 2018, we get a very different story. The proportion of crashes in rainy weather is 2 to 3 times higher than the proportion of time it was raining, particularly in these hours of darkness. Hold this thought. Let's go back to this for a second. If we look at this as the raw number of crashes rather than percentages, we see something interesting. The total number of crashes, that's the blue and the purple together, decreased in these 2 years, 2020 and 2021, and increased back up a bit in these 2 years, 2022 and 2023, which is consistent with the traffic volume post-COVID. Remember this! We saw a dip in traffic volume and then a recovery back up. Now also remember this strong La Niña event in these 3 years, 2020 to 2022. I think this aligns with what's going on here. According to the Bureau of Meteorology, La Niña in Australia typically means more rainfall and cooler daytime temperatures. This is where we see both the raw number and percentage of rainy weather crashes increase, despite total crashes and traffic volume being lower than pre-COVID years. 2023 came out of this La Niña event, had a neutral few months and transitioned to an El Niño phase, and we see this reduction in rainy weather crashes, which is more consistent with the other years outside of the La Niña event. I have a few ideas on why more rainfall in La Niña years would mean more rainy weather crashes. The first thing is that there's more opportunity to have an accident while it's raining. Let's bring back in the percentage of days rained. In the years outside of the La Niña event, it rained 33% of days. During the La Niña event, this went up to 46% of days, a 40% increase. The second thing is the road conditions are likely worse in La Niña years due to heavier rainfall. This is rainfall in millimetres from the Sydney Observatory Hill weather station. In the years outside of the La Niña event, it rained an average of 939 millimetres per year. During the La Niña event, this average doubled to 1,790 millimetres per year, predominantly driven by the extreme rainfall in 2022. And if we do one of these, yikes! Anyway, the point is, this 2 to 3 times higher proportion of crashes was from 2018, a neutral year in the El Niño cycle. This is potentially worse during strong La Niña phases if the proportion of rainy weather crashes increases with more rainy days and more rainfall in millimetres. Shit, that's crazy. But what is it about rain that causes a higher rate of crashes? Is it the riskier road conditions, or is it how humans respond to or don't respond to these risks when driving? Research from 2007 suggests it's both. On the one hand, rain causes impaired visibility, slipperiness, and potential road obstructions, and extreme rainfall can cause hydroplaning, flooding, landslides, hail, high winds, and lightning. On the other hand, drivers don't adapt enough to wet weather conditions. The research breaks this out into 4 reasons. Safety isn't always the primary concern for drivers. They may be more concerned with getting somewhere on time. Slipperiness isn't always visually obvious. Inappropriate behaviour like speeding doesn't always give the driver sufficient feedback on how slippery it is. And there's probably a substantial variation in drivers' abilities.
Oh my god!
So to summarise, does rainy weather put more vehicles on the road? At a handful of locations. Otherwise, there's fewer vehicles or there's no significant or credible difference. Does rainy weather make traffic slower? Data points to yes. Does rainy weather cause a higher rate of accidents? Data points to yes. Does this amount to traffic being crazy in rainy weather? I think all of this has helped me narrow in on what this crazy feeling is. Okay, so there's not necessarily more vehicles on the road in the rain. Slower traffic is on the mild side of crazy, and accidents is on the extreme side. And I think in between here, there's all sorts of crazy, like cutting cars off, failing to give way, and hoons tailgating that aren't captured by the data that we looked at, or even measured consistently at scale. Are these behaviours statistically different in the rain? I don't know, but I do think how we perceive them changes when it's raining. I asked around my friends and peers, and most agree that traffic is crazy in rainy weather. But more interestingly, people have differing levels of comfort driving in the rain. I think it's this clash between those who are comfortable versus uncomfortable, those who do adjust their driving versus don't, and everyone in between that makes us feel like everyone else is behaving crazily. Here are my learnings from all of this, and maybe I can reframe how I feel about rainy weather traffic to something healthier. I should probably adjust my driving more in the rain. If it's not obvious how slippery or dangerous it is, it's probably better that we're all going a bit slower. Be kind and accommodating, especially in riskier conditions like at night or on motorways, because there are some people who are uncomfortable driving, and reacting to maybe inadvertently bad behaviour only adds to the tension. I also think maybe I project a sometimes feeling to, it's always crazy when it rains, and I should stop and think, was it actually crazy this time? And lastly, if it's a La Nina year, I think I'll just stay home because my findings were pretty scary and it's crazy out there, y'all. I came at this from the angle of how crazy is rainy weather traffic, but it raises other questions that answering would be beneficial for all of us. Like, is driving even a good mode of transport in different locations in rainy weather? Does public transport usage change? Can existing infrastructure handle moderate and heavy rain days? Where does it need to improve? Anyway, thanks for making it to the end of the video. If you liked it, please consider subscribing and liking. Every little bit helps. Before you go, I want to hear from you in the comments what you think of traffic in rainy weather. And before I go, please enjoy one of my favourite things about the rain.